So let's start with my training. I will try not to touch the metallic part of the laptop. So I guess that everybody here knows what Radare is, but I will make like a quick introduction. So I will also explain how to use the shell, how to analyze stuff, how to do debugging, patching binaries, and scripting. So what's Radare 2? Radare 2 is free and open source software. I wrote it in my spare time, so selling it or doing anything like that. It runs everywhere, so every time that I'm having my hands in new hardware and trying to port it there, it's running in all major operating systems like Windows, Mac, Android, Linux, and so on. But it's also running in QNX and as well as iOS or iOS. It's easy to script it. There are so many ways. I will later explain how to do scripting with R2Pipe, but I will explain also there are many other ways for scripting, like using it in batch mode or in a basic shell script, or you can also do it in any scripting language using the native built-in for the APIs or also R2Pipe. It's easy to embed. It's basically a framework of different libraries. Each library has plugins, so you can extend the functionalities of these models with your own code. All these models are connected between them. I will later show they are connected. So you can extend the functionalities in different ways, not just by scripting it. You can embed it in any other application. You can just statically or dynamically link the code libraries to the program. It grows really fast, so every release comes with like 1,000 commits or stuff like that every 6 weeks. And so, like for example, every day I'm having 3 or 4 pull requests in the GitHub page, which is really nice. I mean, it was not like this 10 years ago or 5 years ago. So I'm really happy to see that there are so many people using it and pushing their code. And well, my work nowadays is more focused in trying to teach people how they should be coding for Radare, or how they should be following some coding standards and so on, or making secure coding in C than coding by itself, because I have so many contributions and I have to manage them. It supports tons of file formats. It can load like from ELF, PE, etc. And the thing is that it's abstracting the information from these binary formats in a single logic. So, for example, imports or exports are considered symbols, for example. There is some generic words that you don't have to change your mind every time that you use a new file format. This is useful because if you have some script that is doing some static analysis in random binaries, this way you can reuse the same code in different file formats and it will work the same way. It also handles a lot of architectures. It's easy to hack. I mean, you can just grab some lines for some keywords that you don't know that want to put your changes, and it's pretty easy to find the place. I will make some examples later. It's driven by command line. You can do everything from the command line of the shell, but there are also APIs. Which kind of API you want to use. Well, there is a great community and a better leader. And it's really collaborative. I mean, I'm trying to distribute as much as possible the work and contributions. Radare 2 is a rich engineering tool. It's focused at the beginning, it's focused in forensics. I did this tool basically for recovering some files removed in a HPS partition in a Mac, an old Mac 4PC G3. And I just wanted to, next time on monitor, to open this device and look for some patterns, and then dump the results into disk, and then check which was the full copy of the last version of the file that I was interested in having. But apart from that, I started implementing disassemblers, analysis, debugging backends, and so on. It's a low-level debugger. It's more similar to Oli than GDB, for example. I mean, people using Radare 2 is not using it for debugging source programs. So if you have a program with source code and you want to debug it, it's better to use a source debugger than a low-level debugger like Radare. But it also supports dwarf, so you can see the relation between addresses and source lines. it's mainly focused for analyzing all the backend stuff that you don't have source code for it. It's have assembler and disassembler functionalities for multiple architectures, so you can patch just changing the bytes or giving the instruction that you want to change. So this project started in 2006. It was, this is 10 years ago. So this is the 10-year anniversary of the project. Well, it's 10 years like before. And this is the make data, which is a make target inside the project that generates a graph with all the dependencies. I will try to zoom with it. I show you here. Okay, so here is RUtil, which is the library which provides some utilities. The RUtil is a library that provides basic functionalities like libc, so you can just replace the functionalities this way. So this way, you can abstract from functionalities. For example, there are different libc implementations, and there are some that doesn't implement the stuff that is implementing GNU libc. So I'm just giving the primitive in there. The idea of splitting the project in multiple libraries is to be able to review and refactor in a proper way each of the models, so I can differentiate the functionalities that are important in these libraries. There are also, I will show you in the source code, which will be better. Okay, so you can see all the libraries that are there. There's the anal one for analysis. There is also the SM for handling. There is the bin one, which contains all the binary formats for parsing the headers and so on. The BP library, which is providing breakpoint functionalities. This is basically for software breakpoints. All the hardware breakpoints is implemented in the backend. The cons one, which is implementing courses-like interface, so you can do whatever in the console, like printing stuff and changing colors and so on. It's also a readline implementation. The core library, which is the library which is linking to the rest of the libraries. There is the crypto, which is able to encrypt the crypt, but it's also have functionalities for encoding and decoding. The debug, which implements all the functionalities for the debugger, like stepping, continuing, the hardware breakpoints, memory management, etc. The diffing, which is a library which provides functionalities for diffing from source code to binary stuff. So you can diff like a GNU diff for getting unified changes in a file, but you can also do the same with binaries. There is also the EGG, which is the egg. This one is for, it's like a Metasploit replacement. It's a library for building shellcodes. You have a CAPI for filling paths with knobs, or you can just embed some shellcodes in there. There are also some encoders, like a short encoder and so on. The flags library, which is used for basically identifying a name for a specific offset. So it's like a bookmark or something like that. The file system library, which is able to mount different file systems. Same for partition types. The hashing library, which implements different sections. The AIO, which is implementing the abstraction for all the access to files. Like, for example, when you are opening a file, you are using this API to access it, and this file is mapped in a specific virtual address. So this library is in charge of emulating all the sections, all the memory maps, the permissions for the different memory maps. It's like a MMU. There is also the lang library, which is used for exporting some basic APIs to create bindings from inside the project. So you have a C API for binding a Python variable, for example. Then you can use it calling C code from Python or Node.js, etc. The Magic one, which is implementing the Magic file. This is basically a copy code. The code is copied from OpenBSD. I fixed 2 bugs, reported them. And the idea is that this library is used for doing carving. You can grab any memory dump and carve for known file formats, like just some magic numbers and different checks in the headers. The parse library is used for parsing text, so you can specify some simple regular expression and stuff like that for splitting the keywords and so on. And this is used for generating a pseudo disassembly, so it's basically parsing the disassembly in plain text and generating a more human-readable version of the disassembly. The reg library, which implements all the register functionality. So as you can see, that the debugger implementation here is split in different libraries. So, for example, in I/O you have the trace calls for reading and writing memory, for example. You then have the register library, which is handling all the register profiles, which specify the structure where all the registers are stored in memory, provided by the kernel. There is also the debug, which provides the functionalities for stepping, continuing, and so on. The breakpoint library, which provides a library for giving you the debug API is asking to the BP library for a breakpoint of 10 bytes, for example, and this library will give to the backend another breakpoint that fits in size, for example. And then there is the syscall library, which is used for injecting syscall, so it's able to have the syscall tables for different operating systems and architectures. So you can say, for example, I want to call CCFL for iOS and ARM64. And gives you the syscall number and you can code a call just passing the parameter numbers and it generates assembly. There is also the socket library, which is used for making socket connections. It's an abstraction for Unix and Windows primitives. The search library, which is used for doing keyword searching. That's all. So on top of these libraries, there are different programs that are written that are using these libraries. And the main one is Radare, which is the one most people is using. But anything starting from R and ending with a 2 is something that points to Radare. So Radare is the shell, is the command line of the framework. But there are other utilities that can build some command line helpers for doing some specific stuff in JavaScript or automating it in the shell. So, for example, you have Rabin2, which is a program for extracting information from binaries. You can get information from the headers or symbols, etc. There is Browse2, which is a tool for assembling and disassembling. You can do stuff like that. I will make some short samples for each. So Rabin is able to grab information from the headers. You can also get all this information. So you can get entry point information, you can get symbols, imports, libraries that are linked with the interpreter of the binary. If it's a fat binary, like a fat match of a library or other files that can be considered like fat, like a zip file, any container that can have more than one binary inside, you can extract it. So you can lipo binaries with that. All the commands and tools in Radare are able to export all the information in JSON, which is pretty useful if you want to automate it or extract information and get it with other tools. And you only have to pass the flag. So if you do the same like this, so can you read the command line? And you get the JSON like this. It hurts. So you get the JSON, the information that you ask for it, but in JSON format. Well, you can get symbols. As you can see in Mac or binaries, there is more symbols than any other program will grab you. The reason is that in the macro headers there are some sections that are specifying where is the beginning of each function. This is useful for getting backtrace information when you are debugging. So if there is, for example, all the public exported symbols are considered symbols, all the imports are considered symbols in the PLT or in the address that is used for a trampoline to call the external library. So you get symbols for imports, you get symbols for exports, and you also get symbols for all the internal information from, for example, class information from Objective-C, etc. Then we have the last symbol. I didn't say that, but -L uppercase will show you all the list of plugins that are associated with this tool or library. So Rabin2 is written on top of Erwin library. Rasm2 is written on top of Rasm library. ¿Puedes conectar la correcta? Sí, ya, es que no está en... So using Rasm2 -uppercase L, you get a list of all the supported architecture plugins. And here you have information. For example, the first letter is assembly. So if there is an A at the beginning, it means that it's able to assemble code in architecture. If there is a D, it means that it's able to disassemble. The uppercase A means analysis, so you can analyze stuff for this architecture. And E, the last letter in the first column, means that it's able to emulate. The emulation is done on top of a seal. I will explain this later, giving some examples. But it's basically an intermediate language based on. And here you have the name, the bit sizes of, for example, the ARM is able to, considering 16 like a thumb disassembly. You don't have to specify thumb as a different architecture, just switching from 16 to 52 to start with an ARM and thumb. And there is also ARM 64. There are also some external plugins, so this is only what's going on with the core implementation, but there are some external plugins that you can install later. There is L2PM, which is a package manager for Radare2. It's not only for Radare2, but also for system. The idea is that there are some projects or libraries that are using Radare2 and they are useful, but they are pretty hard to install, or you have to find them in Google or any other site. And I thought that just implementing a simple shell script that is able to manage the packages for that, it will be enough. So I'm focusing on Unix, so I basically am working on OS 6 most of the time, but I also use Linux. But this tool should be working also on Windows Mint to have Mint installed. And well, let's see, for example, this is the R2PM command. You have to run R2PM init, and this will download a repository that contains all the packages. And then you can do, for example, -S for searching, so you get the list of all the packages that are embedded inside. By default, it will install everything in your home, so you don't have to worry about flashing your system directories. But there are different packages here that can be interesting. For example, there are some text to share, for example, if you're reverse engineering binaries, it's useful. I mean, you can download the C repository, copy the jar, put the shell script in your system, or you can just R2PM -I and give the package name. There are also other architectures or some abandoned projects like ARM2, for example, which is a ternary ARM disassembler used for embedding or so on. But there are also other architectures, Alpine-Full, for example, which is implemented by Squatter. Which is an architecture that was used in CTF. There are also support for Keystone, so you can assemble instructions using Keystone library. But there is a Keystone lib package, which is installing the library of the Keystone. So here's the plugins for Radare2, and this is the core library for it. There's support for C#, R2Pipe for several libraries, create something really new and not yet used. And support for the compiling, etc. So as you can see, there's also support for different web UIs. I will show that later. All the web user interfaces are split in packages.
What was the command?
R2PM. Yeah, this one. There is also Radif, which is able to get some text to diffing. This is a bit silly diffing, but I'm comparing two completely different programs. But you can see a bit how it's looking. You get basically two examps from one file and the other one. When it's finding common stuff like padding of zeros or something that is in the same padding two files, it will just show nothing. But if there is something different, it will show some context, and it will say in green, which is the same, and in red, which is different. The nice thing of this is that it's also able to do some diffing, but with some deltified. So you can, for example, if you have the same contents, but this content is deltified in a different offset, it will show you that this file, this stuff is in a different offset. I will explain later all these tools in more detail. There is also Refine, which is able to look for some keywords. So Refine use fetch, leave. It will show you the offset of this string. You can also search for hexadecimal pairs or contents of a file or anything else. There is Radare, which is a tool for specifying the profile for running a program. So, for example, if you want to run a program with a specific environment, or you want to change the CH root or change the ID or the group ID or anything that can affect the execution of a program, you can specify it in a Radare profile file. And then when you are debugging, it will take this file and set up the environment for it. This is useful because this command is also able to specify, for example, if you want to send the first argument of a program instead of playing a string, be the contents of a file or the output of a specific command. So you don't have to build a specific program every time that you want to do this kind of thing. So when you are doing exploiting, usually you want to, or fuzzing, you want to reproduce the same environment more than once. So you can create different profiles for this and generate, for example, different samples of files that are fitting this program for standard input, or just changing the standard input file descriptor to be a socket connected to another server, for example, and stuff like that. So you can abstract and define the environment for a program. There is Drax2, which is a tool for changing different bases. So, example, you put a number in decimal, you get the same in hexadecimal, and if you do the same the other way around, you will get the same back in decimal. The reason for this is because there are some base conversions. You can specify that you want to keep the same base if you like, but this tool is able to convert, for example, from raw binary to X pairs, which is decimal numbers, one is after the other. It's also able to do the same in negative numbers, just folding into 32 bits or 64. You can also work in octal. You can also work in binary. So if you want to know the hexadecimal number of this binary number, you can convert it like this. If you want to get the other way around, you can use like this. So there is a syntax for each conversion. There is also support for floating point numbers, or even for hashing strings or so on. So you can also, this one is useful also if you have a shellcode in a C file. You can slurp it and convert it to the next bit. So it will parse the array in C and grab the numbers. So there is also support for base64. You can swap the endianness. So if you want to get the swapped endianness of a specific value, you will just do it with -e flag. There is also R2Agent. The R2Agent is a small program that is running on top of rutil and RSocket. It's basically providing a web user interface for spawning Radare instances. The thing is that if you have a router, for example, or a embedded device, and you want to start debugging stuff in there, you can just spawn the R2Agent, which will be running all the time, and then you can connect Radar to this device, to this service, and you can upload files, you can launch a new session of Radar 2, and it will show you which port is listening, so you can connect to this port and start debugging or talking to it directly. RAC2, which is a program on top of the egg library, the one for generating shellcodes and so on. So this way, you can see that there is only one shellcode. The same thing for Radar 1 was like a pretty huge list of shellcodes, but in Radar 2, there is not much people using it yet, but we just took use of doing it just as an example. So it's basically an exec shellcode, which is you can specify the command that you want to run, and it will generate. The thing is that this shellcode can be defined by some parameters, so you can specify the architecture. You can say you want it for MIPS or ARM or x86, and you can also specify the bits, and finally the kernel. So you can specify the operating system. So it will generate a different shellcode depending on this command line flags. As you saw, the -A and -B flags are pretty common. I mean, they're used in all the other commands. So -A will specify the architecture, and -B the bits. So this will be useful, for example, if you want to extract FAT binary from inside the FAT binary. You can specify which subbinary you want, like and to open the PowerPC subbinary and specify A, PPC, -B32, and then the FAT binary, and it will open only the PowerPC binary at the FAT. There is a hash, which is a tool for hashing stuff. This is useful for forensics. So here is the list of all the hashes supported. The thing is that you can hash in different ways. You can hash in a stream, you can hash in 5 blocks, you can hash in a single block. And the good thing for this, I mean, for forensics, when you are, I don't know if you have been working in forensics before, but one of the most common things is that you are hashing like 1 terabyte or 2 terabytes of data, and having a single hash for all the data is not really useful because it takes a lot of time to compute, and if you change a single bit, it will be messed up and you will not be able to identify what has changed. So you can specify the block size and get, for example, 1 hash for each megabyte, and at the end you have a list of all the offsets, the range of the bytes that are hashing, and the hash for this block. This way, you can have, for example, if you have a memory dump and then you generate another memory dump, you can just hash the blocks and then compare the hashes. And this way, you can quickly identify which parts of the memory have been changed. You can also do this with Radif, just checking which have been changing. But if you are managing like huge, like 4 gigabytes or stuff like that, it's easier and more useful to do it like this. This is all the list of checksums. There is also able to support for encoding and decoding. There is base64, base91, and Unicode. There is also support for crypto.
One question. So you can chunk a big file and hash it with rahash itself, or do you have to chunk it separately?
No, it's rahash is able to chunk it. So you can pass a 4 gigabyte file and specify that you want to generate a hash for each megabyte. So if you specify all, it will hash the file with the full file with all the hashes supported. You can specify only one. As you can see, there is also entropy computations, the having distance, MD5, so on. But as you can see, the offset range of the section is the full file. You change this with the minus D. You can change the block size. So here we have the MD5 of every block of 512 bytes, and you get the hash at the right. As you can see, this way of hashing is useful because this way you can also find common patterns or stuff filled by zeros or stuff like that, because you are seeing like repeated hashes at the same at the end. And if you specify the entropy, you will get the entropy graph, which is showing you basically the entropy computation of each of these blocks. You can change the block size and get a different graph. But this is useful because for entropy calculations, you will get information, for example, at the beginning, there is low entropy because there is the headers of the binary, which contains usually many zeros or many repeated bytes. When there is code, it's like a medium entropy. If there was a compressed stream or encrypted data, it will be almost getting there. And if there are strings, it's pretty low entropy computation, so get something like that. So here are the strings. So with the strings you get this, and this is binary data at the end. So we have higher entropy. And well, there is also Radare. It's able for doing getting some signatures and generating signatures like Bill is doing for IDA. There is a man page for each of these tools, and all the source code of these binaries is under the bin.r directory. As you saw before, there was the source code for the libraries inside the bin.r libr directory. In the libr directory, you have the bin.r directory, which contains one directory for each of the programs, and then there is the libr directory containing the libraries. Okay, so what can you expect with Radare? Well, there is people doing stuff with Radare from many different fields in security context. There are support for disassembling Apollo 11 CPU code. There is also support for analyzing iWatch applications, or there is also some people asking me supporting DNA sequence analysis, basically for recovering sequencer machines from corrupted tabs. There is also for CPS support. This is the Street Fighter cartridge. There is also doing some Pokemon Go reverse engineering. The other two, also some people emulating parts of the code of Tamagotchi, Game Boy ROMs, ABR ROMs, etc. Well, this is a mainframe. So as you can see, there is support for so many targets, and you can use this tool for very different fields. So the thing is that the way that you access these files can be in very different ways. And the other two is built on top of some Unix concepts, which is everything is a file. There are some other Unix file specific context I try to follow. And one of them is that everything is a file. So accessing a process is accessing a file. Accessing a remote device is also accessing a file. So you have like a abstracted file system access with some URL path. So you have, for example, HTTP // or to pipe for accessing remote streams. And it's also able to load from executables, libraries, file system, role memory dumps, devices, work devices, etc. You can list all the EO targets using R2-L. Like I said before, that if you use -L in uppercase, you will get the list of plugins. And this is the list of plugins that Radare2 is able to open. So, for example, you can talk with a box debugger. You can also connect to the native debugger, which is dbg //. This will, if you start debugging like this, you will only be able to access the memory, not be able to step or do anything like that. To step and do any other debugging related task, you have to attach the debugging plugin connected to the IO. And Radare2 is able to do this just specifying this flag. So if you want to debug, just -D and you will start debugging. Other interesting IO backends are, for example, the GDB. So you can talk with a remote GDB session. There is also support for gzip, so you can open gzipped files. You can get files from HTTP. You can also open EX files from, mainly for EPROM tools or microcontroller ones, which is a text file, and you can open it directly with Radare2, and you will get the binary contents of that. The Max debugger, which is the low-level debugger for the debug. So this is basically an abstraction for all the debuggers, and then there is one native implementation for each architecture, for each platform. The malloc one is really useful, mainly because if you do R2 minus, just a single dash, you will get the prompt, and you can see what's open with the O command. I don't know if you can see it at the end. The O command will list all the open files. So if you open R2 like this, you will basically get a half kilobyte malloc block that is filled by zeros. So you have a playground here for testing different comments, writing stuff, doing anything else. So for example, you can just write hello world, and get the extent like this. The idea is that you can then do whatever you like in here. So for example, you can open a malloc URL and then grab the contents of a file and put it in there, or whatever you like.
How do you do that?
The X command for dumping or the writing?
For the command?
Well, use R2 minus. Just like this. If you want to open Radare2 without opening anything, you have to do the same, but repeating the with double dash. There is no open file here. So if you get the extent, you will get. Okay. So there is also support for F2K. This is only working Linux and Windows. Basically, it's an interface for talking to the kernel. There is a kernel model that is loaded in the system, and then it creates a new device. Radare2 is able to read, write memory from kernel, and also specify which process you want to read and do some. The idea is to be able to debug and analyze stuff without using the kernel primitive. There's also support for R2pipe, so you can use R2pipe files for implementing. For example, you can write an IO abstraction for accessing some remote resource in any language supported by R2pipe, JavaScript or Python, etc. That's more or less the most important ones. And self is also useful if you are gonna embed Radare2 inside other programs, or you want to use debugging. The thing is that this way it's opening the self process. So this way is Radare2 This is the memory maps of the self process. You can, for example, jump anywhere. Jump it. You can also write memory. The thing is that if you are writing outside the memory range that is not able to write, it will not crash because RadareCon is detecting which is the ranges of memory that are valid. So the processor will not crash. But this is basically RadareCon loaded inside any other process, like a shared library that you are injecting it. And you can also do this with RadareCon. Said before that you can specify some environment. One of these environment specifies that you can preload RadareCon inside any other project, any other application. So, doing example like this. So this is cat running. If we send this signal, which is just copy pasting the command that is there, you will get the shell of RadareCon. So you can also use the same commands that I showed before for listing all the maps. You can modify the process in memory, etc. I added some commands for injecting code in there, so you can also do it like this. So you can say, for example, that you want to run the program for some time and then get the back shell. You can also call some specific function or symbol, and you can specify the arguments for calling this program, this function. You can also send field signals, etc. Okay, so let's talk a bit about the command line of RadareCon. As I said, RadareCon is copying or grabbing some Unix concepts. One of them is the files, and other ones is that there are some little programs talking to each other by using the pipes or different communication channels. And everything is text, so you can read it like plain text. So this is useful for debugging when you have some wrong or you are just copy pasting some stuff. So it's trying to do everything in plain text. In the shell, you have some special syntax, which some of it is common in the POSIX shell in Unix systems. So, for example, you can use pipes. This will redirect the output of the command to a system program. You can do stuff like that. So, if you are doing extra or PD for disassembling, that's something for. Okay. So you can disassemble like this, and if you use the pipe, you can send this to less, for example. So you will get less program working with the output of the command. There are also redirections, so you can pipe the output of the command to a file in the file system. You can also use backticks. This is for embedding the output of a command inside another program. So you can do stuff like this. So you want to disassemble 3 instructions like this. And you can grab the output of a specific command like this. There are 6 instructions, and compute it like this. This is a still example because you can just go directly here. Because every command that accepts the numbers also accepts any other expression. You can use parentheses, you can use multiplications, ifs, also names. So if you have a flag like this, you can use it in any math operation. this. There is also some internal filtering. The reason for this is that you don't usually have grep in all the systems. So if you want to grab some stuff, you can do it directly with this sign, and it will work in any operating system faster than using the system one. So if we are, let's open BNLS. So here we have the entry point of the BNLS program. We can analyze it. And what we want to do here is that we want to get all the calls of this function. So we can just do PDF for showing the disassembly of this function. And if we use the internal grep, we can grep for call. Right? So if you want to grep for any keyword, you can put the expression at the right. You can also count. So for example, let's see how many calls are in this function. You can just get the number. Another thing that is coming from Unix is that everything is self-documented.
How do you apply regular expression?
There is no support for regular expressions. There is support for regular expressions in searching, but not in graphing. You can also get for columns, for example. Lines here. Something like that, and you can type it. Get all the instructions that are in this function. So the idea is that you can mix different commands in Radare2 to be able to extract or to filter and map all the information that compressed inside the tool, and mix it with other tools from the system or scripts that you're writing inside the command.
If you want to grab all the symbols in all the program instead of just function graphics, then it will be what squiggle.
If you want to call, I mean,
all the functions in this library.
They are asking.
You can disassemble the full file and then specify that you want grep for the symbol name, and you will get. I mean, it's just object dump, pipe to file, and then.
Okay.
Carefully.
Okay.
So, don't use it whole room and everything. But this sound is going in that room a lot.
Really?
Yeah.
Okay. Can you hear me the back? I will not get electrocuted. Okay, so as I said, everything is a file. You can pipe stuff from the shell to the shell. Everything is self-documented. This means that you have a man page, and there is also the question mark. The question mark is in any comment. So, for example, if you type question mark like this, you get the help, the core help. But as you can see, there is only one letter for each comment. So, for example, as I said, there is X for exdump and P for printing stuff. So I use PD for printing disassembly. I can also use PX for printing exdumps. Mainly, if you have X, you are dumping, which is an alias for PX. So if you want to get the help for P, you can just press P and then the question mark. You get all the subcommands from P. The idea is that it's like a tree of all the commands, each letter specifying as a subcommand, and you have help in all the subcommands. So when you are looking for something and you want to do something, you already have to understand these basic concepts of having like each command is one letter, everything is structured in a tree of commands, and then you can specify or get help of all these commands. You can also use grep, internal grep for grabbing the help of each command and look for what you are looking for. So And finally, there is also support for some basic PostFix shell commands. It's a massive box replacement. You can type ls, you can type pwd, etc. There is cp, mkdir, rm, or Unix commands. And there is also support on sandboxing. Radare 2 extracts all the wraps, all the calls that can modify system files or executing programs or anything like that. And you can disable it like. Wait, I cannot. Work. Running from the shell like this. This is not working because I haven't enabled the sandbox mode. This is useful. I mean, it's not using the system sandbox. This is a software sandbox. It's basically abstracting, wrapping the system close to a system. There is also some documentation explaining how to do sandboxing in system side, but this depends on the operating system. So there is some documentation for OpenBSD or for Linux, Windows, OS X, etc. So if you have Radare 2, you have like a full shell for working. Like I did a live city Linux image that was basically spawning R2 in the init. So you get a shell at the beginning of after getting the kernel, and you can ls, copy files, edit files. There is also an ED editor inside, so you can edit text files also. So let's first make a poll to see how many of you, which is the main operating system that you are using. How many Windows? Only one. How many Linux? Most of them. How many OS X? Okay. I'm not gonna ask for SD. Sorry. Okay, so do you know how to use Unix? I guess that there is only you're a Windows user, but you know how to use Unix. You'll understand most of these concepts. How many of you have used Radare 2 before? Most of the people. So let's begin with installation. This is a tip for professional people. The best way to use Radare 2 is by installing it. So if you don't install it, it's difficult to use it. So there are so many ways for installing it. You can use the live CD, which is maintained, and before I remove it. It's just a shell script that generates a live image. It's complex stuff, but nobody using it. But it's nice for forensics like that you have like a small live CD image for rather analyzing binaries or doing anything right in a probably file system. There is also a 6 package, which is updated after each release. There is a Windows installer. There is support for BSD and different systems in the package system. The Debian packaging is really old. By old, I mean that the last version of Debian, I think it's 4 or 5 years old. It now secured that there is a Debian maintainer, which is building the packages, and he will be pushing into the official repository soon. So after each release, in 24 hours or 48, there is a new package in this GitHub repository, so you can just download it and it will work in Debian. There is also the cloud web user interface. This means that you can use Radare 2 website. You can also, I can try if it's. You can also install it in Android from the marketplace, and also in iOS there is a CDA package, or you can file it full shell script. And finally, you can use it in Telegram, a bot called R2 bot, and talk to it, and it will run commands. This bot is running in a sandboxed and seed-rooted system, and it's running in sandbox, so you can do mess with the system. But if you want to check for some help or assembly or disassembly stuff in different architectures, from Telegram is pretty useful. We need to know anything have anything anywhere, just having a Telegram shell. And well, we have Travis and PA for building packages automated. For installing, you have to type these comments. First one is git clone for cloning your repo. And then you will enter the directory and run this shell script. The reason for running this shell script is because most people is having problems because they don't know how to build software in Unix systems. So explaining how to run, configure, and then make is really tedious. And after some years of having to explain how to run, configure, make install, and having people with problems like this, I decided to write a shell script, which is basically cleaning the build system during git pull, because people always forget to run git pull and they are complaining about really old bugs that were already fixed. And then there is a sys user shell script, which is doing the same but installing in your home. You can also run Radare 2 without installing it at all. There is an M. There is an M shell script. I import it like this. So here you specify the path of the Radare to install. And you can specify then the programs. So this way it's changing the library path for looking inside every of the directories of the system, in the source directories of the Radare 2, and changing the path for following to get from the inner directory. So this way you don't have to install it for just. The way that Radare 2 is built is on top of ACR. ACR is an autoconf replacement that I wrote in shell script. So it's a shell script that generates shell script and runs shell script. And this way you can check for dependencies, specify the prefix path, test dir, so whatever you need for your build system. And the thing is that this is the final generated file shell script is about less than 100 kilobytes, and the GNU one is like half megabyte. So I was not understanding the reason why I have to maintain or build or commit so huge shell scripts. So I just decided to write my own, and this one is working every system. And then I'm using handmade files for the rest of the things. So it's not using automake or anything. If you want to choose which plugins you want to build by default, you have to use configure plugins or just replace this script. This is the list of all the plugins that are statically linked inside the core libraries. And then this is the list of the plugins that are compiled in a shared library. So when Radare 2 is spawning, it's all the core libraries can be containing some plugins, and some other plugins can be just in the file system. You can put a plugin in your home or system directories and in plugins from there. But if you want to make like a smaller size build of Radare 2, you can copy any of these. For example, if you want to build Radare 2 in script and for JavaScript, you can copy this file to this. And then run make, and it will build it like that. And same for Tiny or NoGPL if you don't want to have any GPL stuff in your build. So there is some code copied from. You can just take it from there. There is also some documentation in the doc directory. As I said, there is sandboxing information, how to debug brainfuck, diffing, cross compiling, etc. And the sys directory, there are some useful shell scripts that can be handy for building Radare 2 with different targets. So, for example, if you want a build for Android, just run sys Android MIPS, and it will check for the NDK and build everything. You can also make paths and reels for fuzzing. You can also walk, and this kind of stuff will be moved to R2PM. And this is the shell script for building for iOS. For the CDA package, for simulators. Same for Windows. Same for 6 packaging. It's mainly some random shell script that can help in packaging and stuff for yourself. So let's take the R2PM. How can we use it? If I run R2PM-L, it will list the packages that are in my system. Just install again. It will be speed pulling, so downloading the last version of it, cleaning up and running and installing. So right now I should be having the Keystone plugins in version 2. Yeah. And you can install else. Okay. Will be working by tomorrow. Okay, so after this, well, you can also update package database. It's in Radare 2. If you install Radare 2, you will get the R2PM. And finally, if you want to manage Radare 2 from R2PM, you can also do that. So you install Radare 2 from R2PM, and then you remove the installation. Is that by default, Radare 2 is installed using symlinks. Like, there is Radare 2, and you see what's in there. This is a symlink to Radare 2, and Radare 2 is a symlink to. The reason for this is because most of the people that is using Radare 2 is also fixing stuff or developing or extending the functionalities. So this way, they don't have to install all the time that they make a new change. So when you are changing, for example, we are going to change. So for example, we want to make Radare 2 smile. So just start make. I don't know. But you don't have to install every time because everything is installed using. This is okay for single user system, but this can be a problem if you are installing server, for example, that have many. And this is the list of other packages that can be installed in testing, like Yaga 3, signatures. There is Radare, the compiler support. There is Keystone, Unicorn for emulating code, native Python bindings, Polo 11 CPU, Ducktape for JavaScript scripting, Radare the compiler, which is a working progress the compiler with a little more at the end of the talk. Different implementations of R2Pipe, etc. So let's start with the comments. Radare 2 have some interesting command lines. -H showing the help of the Unix comments. One interesting thing of Unix is in Radare 2 is that I'm using the POSIX getopt SQL. This means that when you are specifying the command with flags, you have to specify first the flags and at the end the files. GNU getopt allows you to mix this, so you can specify first the directory or the file, and at the end the command line flag. This is not good because this allows you to do some messy stuff, and in fact, if you compare the number of lines, implementation of getopt long and it's silly. So I decided to use just the plain getopt, which is working everywhere, and it's pretty easy. I'm trying to use only one header for each flag. And we can specify the architecture -A, -B for bits, -C for running a command, -C for interpreting a script. So, can write this script, for example, which is using it to pipe. This line is opening the self session, so when you are running this from inside Radare, it will open reuse the same session you are using right now, and then run a command. And this command will get the output. So if you want to run this script, we can just do it. So we executed the script. In Python, this Python script is using Radar to pipe for talking to Radar 2, and it's running at the beginning. Here, if you want to run a script, we can use dot. Yes. And let's see the most common commands that you will be calling Radar 2 or so on. By default, Radar 2 it's opening the files in read-only, mainly for avoiding disasters. So if you want to write a file, you have to specify with -BB, and for example, like this. This is an empty file; doesn't exist yet. So I can write some experts like this. I will quit, and if I check the size, 3-byte file, I open it again. You will see the 3 bytes that I wrote before. So Radar 2 is able to create files. It's also able to open a file that exists and write on it. And it's also able to open normal files or block devices. So if when you are opening a this device, you don't have some constraints, but you have to make it read from some specific block sizes and stuff like that. And Radar 2 is able to abstract all these kind of complications. Same for bitrace interface that you have to make it in a size and so on. And when you're opening a file, like for example bin.ls, you get at the beginning the entry point, the virtual address. The thing is that if you want to open the file without understanding or parsing the headers, you have to specify -n. This way, you get the offset at the 0 offset, and this is at the beginning. So it's mapped at 0 address, it's not mapped at any virtual address. And this way you can patch the file in the same place. If you open the file with like this, so open ls and opening in the right mode, I can see a disassembly, and for example, I want to not first instruction, and I can do it directly from virtual address. So Radar 2 is able to translate the virtual to physical addresses and the other way around. You can also open more than one file. So as I said, the I/O library is abstracting the layout of the process of the binary or the file that you are opening, and you can do that. You open the binary like this, get the shell, and here you have the I command, gives you all the information from Rabbit. You get the I for getting the information from headers, IJ for getting it in JSON mode. There is also the grep here that you can, if you do this, you will get JSON information. And if you do it like this, you will get JSON and less. You can go up and down. All this information, so for example, the symbols or the sections, all the symbols, firing. You can get also the imports, that's the name of the import. You can get the libraries. You can get the entry point. If you specify the queue, it means white. It will only show the information that is useful for this code. Verbosity and stuff like this. So you get the base address, load address, the physical, etc. And this information, if you specify at the end of the command question mark, you get the help. If you specify the queue, you get the white output. If you specify the J, you get the JSON output. And there is the asterisk, which will show you information in other comments. So, for example, if you specify like this, you will get the I information, so the hidden information, but in other comments. This means that these are the comments that are executed by Radare 2 when you are opening this. It will specify the endianness, the bit size, if there is wife information, which language has been written this program, what's the operating system architecture, and the same for symbols. So if you get the symbols like this, you can specify the asterisk at the end, and you get all the comments that Radare 2 will be running to import this information. If you want to import this information, I mean, you can copy paste this and paste it in the shell, but it's quite primitive. You can just prefix with a dot. As I said before, if you use dot, you can press dot space and then the file name, and this will interpret the file. But if you don't put the space, it will basically run the command at the right and get the output and interpret it. So if you run like this, it will run all these flags to the shell. So you get tab auto completion for like sim.func. You can see there. And also the section information. This is the command I run. If you run this, you will see that there are more information than just flags. The flag is a bookmark, which is giving this name to this offset, this size. You can specify some more attributes, read, write, or other specific comment, etc. There is also comments. The CC command is used for adding comments into this assembly. And there is the uppercase S command, which is used for defining a new section. If you see the output of EIS, you will see that there is some permissions to the right. So you get EN, which means that this section will be mapped by the loader. And then you have the read, write, execute bits that specify the permission. So only the sections mapped with M will be loaded into the Radare 2. And you can get this information using the uppercase S command. So you get this kind of graphic output. The executable parts are in green, the data is in red. You get the idea where everything starts and where everything ends. Yes. Do you want to make a break, like 5–10 minutes for drinking, eating something? Now they can.
Go ahead.
This is the information for sections. You can add and remove. The sections are basically mapping some physical address to visual addresses. This way, the S command, it will say that this asterisk means that you are there. You are moving to another section. And you will see that the asterisk is moving to another place. And here you have the size. The size in virtual memory can be different, and the physical and virtual address. So you can get any file and split it in different sections and map it in virtual memory inside Radare 2 and read it like it was mapped in memory. Okay, more syntax sugar is that if you prefix a command with a number, it will run this command 10 times. So, for example, if we use X, the argument of the comments are usually modifying the comment. So the px accepts a number of bytes, can also use P8 for getting experts. This. So if we want to run this command 3 times, useless or less, you can just prefix it with 3. But there are also other cases, like you want to run a script 3 times or kind of things like that. You can just do it like this. There is also the at sign, is used here, and this is a temporal seek. When you are seeking, which is the S command, you can seek in relative or absolute addresses. So you can, for example, seek 1 kilobyte forward. You can seek 1 byte. You can also seek an absolute address, and this is changing the prompt. But if you just want to get the output of a command in a different offset, you can do the same. For example, bring PD3 here, but you want to do it here plus 1 kilobyte. You will do it like this. As you can see, the expressions are also understanding the kilobytes, megabytes, and all this kind of thing. The dollar sign, it's an internal variable. That is help for all this. And get the help with question mark, dollar, question mark for this. So dollar is here. That is the current offset. And there are other internal variables that are useful. For example, if you are in any random place and you want to know the beginning of the function or where you are disassembling, there is a variable for that. There is also a variable for showing the destination address of the jump or the instruction that you are disassembling right now. The physical address of it, the section offset and section size. So for example, if you want to disassemble the full section size, you can PD in D uppercase. This will disassemble 3 instructions and this will disassemble 3 bytes. So if you want to disassemble the section size, and seek at the beginning of the section. And this will run a lot of lines and you output here. The reason why this is slow, so 1 second, something like that, is because it's analyzing all the code, printing some colors, calculating, computing all the lines, adding some comments. These comments sometimes mean that it requires to read the destination of the memory, read the contents that are there, check if there is a flag in this offset, and then show the flag name. Check if there are comments. There are so many computations in the main disassemble loop. So there are more than one way to disassemble. So you can PD with this. You can also PI, get just instructions. You can also PID to get the disassemble with some more output. So depending on your needs, you can use different comments for that. And finally, you can concatenate more than one command using the line. And it will show, for example, if you are debugging, you can see, for example, 3 instructions from the entry point, from the program counter, and you can get resistors, back, and disassemble. In just one line, you can get the full debugging build. And this is, in fact, what the visual mode is doing when you are debugging. I will show you later how to use the visual mode. But for now, it's important to understand the 3 basic commands, which is seeking, reading, and writing. We have seen the seek command. You can use the add command for doing temporal seeks, not front. You can also use P for printing stuff. You want to see different print modes. Here's the computation. There is also other commands like A. There's also this view, which is 2 characters are 1 instruction. So this example is expressing each instruction by byte. So each byte of the example is a single instruction. And you get an overview of the most of the program. Here you can make the more. At the right, you know how many bytes are in each row. So here you have like an overview of the full program, binary that you are opening, and you can see the moves, for example. You can see the shifting operations. You can see the jumps, the condition. If it's conditional jump, if it's an invalid instruction, it's in red. You can stick around, see how the program is structured. Also, the PXA will show you this this colorful view of the extent. This means that every time that there is a flag, it will change the color. So when you get this kind of extent, you can really see, for example, if you are loading the headers like this. You will get a macro header here and the different segments. Where's the beginning of each command, etc. So this is useful because this way you can have a colorful way for understanding or defining some new ranges, like some bytes and change the color or flag name, etc. The internal grep, I explained this before, but I will samples. Here's a help for the internal grep. You can use for negating a conditional. So you can, for example, grep for all the instructions that are not calls. You can grep for just count the matches. You can use less. You can indent JSON, as I said before. You can also specify which column in the disassembly or the exam you want to graph. You can also get the lines, just like this. And you can also use the dollar and sign. Specify that you want to. It's like a tiny version of a regular expression. It's just checking if the beginning of the keyword is a hat like this. The line will start like this with this keyword. And if you end the keyword with a dollar, it means that the line must end with. The flags are bookmarks, so you specify a name for a specific offset. You can say that the potato flag points to this address plus 1 kilobyte, and you can check the value. And then you can also. So everything in all the bookmark information is stored in different flag spaces. So you can, for example, grab all the strings. You have a flag for each string. Take, for example, here, at the extent. So Radare is loading each string inside the binary as a flag. So you had all the references inside the. Well, and this question mark allows any other kind of operation. You can also specify that you want to read the memory in a specific offset. The question mark is not just for evaluating operations. There are also some other useful. For example, if you want to make a script that is asking the user for some stuff, you can do this. And you will get the prompt asking for something. You can also make a yes/no question. So you can just press yes/no, and you can then make conditional comments. Then the comment, and you can also make echo, and you can also get Clippy here saying hello world. So that's useful for some scripts and get the fancy output. There is also for benchmarking. So question mark T, you get the time that it requires to run. Okay, so let's configure Radare2. Radare2 have the E command, which allows you to specify many configurations for almost anything. If you press two question marks, you get the help. You have a description. And here you can change, for example, the architecture. So changing asm.irh. You can get, for example, a list of them with question mark. So we can change this to ARM and get this assembly of code on ARM, which is useless. You can also change the bits. It is 64 bits, so if you want to get ARM, get it like this. We can also change the zoom mode. We can also change the endianness. There is also, for example, other flags for changing the screen output. You can specify that you want to output in HTML, you want to remove colors, you can change the color palette, etc. You can also change the wheel speed if you want to scroll faster or slower. There are all different graphics. For example, the SCR is for screen. There is search for changing search options. You can search, for example, only grabbing for keywords a specific alienated blocks. You can change the, for example, some key bindings for visual mode. You want to use it for debugging. Options for I/O, options for graph, HTTP, file, directory, debugger, comments, etc. And then there is a lot for this assembly. So if you want to remove the comments or change or remove the bytes, this assembly here, you can add the bytes 0, you get the columns of bytes. And also change the width, you want to change the lines. The lines at the left shorter. You can change the want something wider, etc. As I said before, all the comments can be suffixed with an asterisk. So you can dump the configuration that you are running right now to a file and then interpret it later. So this is useful because this way you can just reuse some configurations. You can also use projects, which is a way to save all the information in a single Radare session to a file and then get it back. For the printing, there's different print comments. These are the most useful, or the most common ones. If you are, for example, doing it like this, you get this assembly the example. But if you want to get this in different grouping, you can group it by words, but also can group it by keywords. And as you can see, there are some colors here. These colors mean something. What it means is, let me check, for example, in the target, which is I'm running pxq to get the keywords of that are contained inside the memory pointed by RSP. RSP is a flag which is loaded from the registers. So it's importing the information from the debugger into Radare 2 as a flag. So if you run it like this, you will get this information, which means red means executable, blue means data, and yellow means read-only data. So if you have a memory dump or just any random place in the heap and you have different structure with different pointers, you can use pxq to understand where is this each pointing to. There is also support for pxr. It's showing not just this, but also some more information. So you get the offset. This means that it's executable. This is the contents, if there is some string or some printable characters in there. And then it shows the section name and the instruction that is pointed in address. For other cases like this, for example, you have pointers to strings. Here, execute another string, and it here, and then it tells you which is the coding. If it's ASCII, UTF-8, 5 characters, etc. This is really useful for rope chaining when you are writing an exploit. Niterman will use this command later in the afternoon. But this way you can, if you have the full chain in the stack, you can use pxr in the, to do this block, and you will get all the instructions pointed there. So you have a linear way to understand what's this doing. Well, you can also print that in a way. That's not very useful, but it's always nice to show. Okay, let's see the pf command. Radare 2 is able to interpret include files. It's able to import this information into Radare 2 and use the pf command to print string. The pref command allows to specify alignment, different type of variables, and you can see, or you can think that this is similar to O10 templates files that are used by some people for analyzing some binaries. And in fact, there is an implementation in Python for this that works in Radare 2. If you go to the Git repo that I pasted before, you can take my code here, and here there is a macro include files. This simple definition, it will parse the header, and it will grab the information from CPU. You can see you can use like these kind of things, but they are type definite, type definition. Define to replace this for a type that Radare 2 knows, which is signating, and then you can also use enums, etc. So let's see how can we import this include file into Radare 2 and use it for showing the data that is contained in the system. We can load with -n because we don't want to parse the headers. We'll parse them like this, and here we can type TO, which is type open, and you can specify there's nothing in the output, but if we type T, you can see, for example, TS will show you the structures. If you type TE, you will show the enums, and if you show, for example, TF, here. If you type P and the name of the structure that you want to show, it will run. You will get this output. This is the PF command, which accepts the first argument is the format string, and then the rest is the name of each of the fields. So if you do PF X, you get this. You get XX, you get this. You can also use keywords. You can also type this and you get all the syntaxes. So you can get these kind of things, and then you can name each of these fields. Have it like this. So coming back to the other example, you get this, but if we prefix this comment with a dot, we'll run this comment. Because as I said before, if you prefix a comment with a dot, it will run the command, get the output, and run it each line as it was Radare 2. So this way you get a magic number, decimal value, you can get it in format. It's also resolving the enum types. So you can see it's U36 the subject any, file type, the number of comments, what is what is the OPF is working. Okay, disassembling. Disassembling is translating the bytes into meaningful instructions. I already explained this before. You can list all the architectures supported by Radare 2 with -L. You can specify with -A, and let's see how to use it. -L with the list, we can sample and 32-bit, and we want to assemble an instruction. An instruction can be an op, different. We can also swap the endianness. And you can assemble different instructions. I mean, if it's not supported by default assembly, because by default Radare comes with some assembler that are not supporting all these possible instructions, just the most common ones, you can use the keystone one. So if you get any instruction, and grab it from here. We want to reassemble this instruction. Then, for example, say that we want to write assembly. We want to change this number 9, and then we can specify the offset as address. Okay, so it's not open. I didn't open the file in read-write mode, so it's telling me that I cannot write that. So one solution will be reopening the file in read-write. Is done like this. This will reopen the file. If you run OO in the debugger, it will rerun the session, so it will kill the process and start it again. And if you're opening a file, you can reopen it like this, or you can reopen it in read-write. But there is also the IO API allows you to define some catch layer, so you can catch the write operations, and when you are doing some read operations, it will fill the gaps with the catch. So we can enable this with 1 or true. And then we can run the command, which is writing the bytes, 7 bytes in. And here we have the patch settings. So, as I showed before, you can get the assembly like this, but you can also disassemble them. Passing -d, and then giving the experience of the. Okay, so for disassembling, I said before that you have PD and P uppercase D for disassembling bytes or instructions. You have PI for showing like a shorter version of the PD, which is faster for big blocks. There is also PAB and PDA. So if you do, for example, like this. The first disassembly is linear disassembly, and the second one is disassembling each byte. So as you can see, it's incrementing the offset just 1 by 1. This is useful when you are looking for instructions on a linked code, only on Intel. But it can be really handy because you can find, for example, some sub-instructions that are hidden inside other instructions and can be used making some internal calls or some tricks for anti-disassembly, etc. And we can use PA like an as rather than, so for example, PA allows you to bytes, and you can also get the other way around using PAD. This is disassembly. So it's a RAS version, but it's using the internal configuration of detector. You can change it like this. Something like that. Right? And for assembling it, this will not work because this is by default assembler. But if we change the assembler to arm.js, that's here. Right. Okay, so there are better ways for getting the disassembled. For example, when you are opening, I have a copy of here.
You can say
say that you can write a memory that is after the batch.
Yeah,
say the file
there is a write cache command, the WC command, that allows you to see all the changes that you have made in the cache layer, and you can then commit these changes into the backend file or dump it into a script file. So you can, for example, cache true, and then you hello world here and blah blah then, and you have the write cache, which shows all the changes that have been done, and you can also dump this in Radare comments, asterisk at the end. So here you can just dump into a file and interpret it when you are loading a file, and it will patch the file in place. So coming back to this demo, we have a random iOS binary here. You get here's a disassembly of the function. At the beginning of the entry point, you get the simple information, but you are missing something from, for example, in RM64, you get the strings pointed in directly in the inside here. But there is some computation that is hidden because when you're disassembling linearly in Radare 2, it's not just disassembling, it's also emulating the code. So each instruction is translated to this kind of expression. This is called the seal. It's basically a fourth-like machine. It's a virtual machine that has two stacks and different keywords. I mean, it's just splitting the expression in by commas, and it's pushing everything in the stack until there is a comment. So you are pushing a register name, another register, and then operation. This operation will pop the last two values in the stack, and it will make the operation. So this means that it will grab the value in PC and set it into this register. After that, it will set this. It will push this number in the stack, grab the PC register, and run this command, which means that PC will change the value to. The nice thing of this is that you can get a lot of information from this simple expression. Human readable, it's just compressed it as in a single block of the memory. You don't have to make like complex structures different for the architecture to represent what an instruction is doing. So you can, for example, change the ASM.emo. And if you enable the emo, you will see what's going on each instruction. So for example, here, it's loading. This instruction here is loading into each one register a specific address. And this address is not pointed by any string because Rabbit was not able to get the string from this offset. So if you're emulating, you are able to get some more information because route will be grabbing this offset and check if there is a pointer to a string. And it will show this there. There is also other handy tricks here because you can, for example, identify when a conditional jump is going to be executed or not. You have this information here. The conditional jump here, and it says that it's likely to be executed. If, for example, in ARM32 or Thumb code or MIPS, it's really useful to have the emulation one of the sides of this assembly because this way you can compute a pointer that is generated by more than one instruction. So if, for example, you are computing, or in fact, you are computing a pointer by two instructions. One that is loading the lower bit of the address, and the other one is loading the higher bit, just doing some shift operations. And if you just, I mean, can be really noisy because you can grab some things like this one or some pointers to loaded memory, etc. So it's really noisy, and most of the time you only want to see the string. So if you enable ASM.emo string, it will only show the strings that are pointed. This is, for example, really useful when you are getting disassembling Objective-C applications, because this way you will get all the Objective-C message send calls. You will get which parameters are passed to each of them. Well, let's explain how I reach this screen. If you press uppercase B, you will get into the visual mode. This mode. You can press P, lowercase, for switching between different print modes, and uppercase P to going back. You are by default in XDump. You press P and go back to disassemble. You go to the next step, which is emulation for debugging. And if you're opening like this, you can step back just with the emulation of the field. So the reason is that, well, I didn't utilize the memory. You can process the binary like this. You can initialize the memory of the serial paper machine like this, and then you get into visual mode, and you have some pointers on serial memory for the stack. You can fill the stack with data, and then pressing S, you can step in. Uppercase S is for step over, and some other keys for we'll explain later for the debugging. But the idea is that Radare 2 is able to debug, emulate, and also do assisted debugging. Assisted debugging means that when you are doing assisted debugging, you are stepping into emulating the instruction before executing. This way, you can catch, for example, doing some software watch points, specifying that I want to step until a specific SQL expression is back. So you're running a program and you want to evaluate if each of the instructions and check when a specific memory is successful. You want to check which instruction is reading this offset. You can do it. I will explain all the debugging steps later, but just giving some examples about the scale and break. Yeah. Okay. So mine was tired. So. Okay. So you can play a little bit with what I have been explaining now. Like 10 minutes. Stop, and we'll continue with that.